we've got a few administrative tasks to talk about before we start doing math material. Okay, so the first thing, my other class asked me to change the automated reminder emails where it reminds you 2 days before the assignment's due. So is that okay in here? Is that too? Okay. 2 days? Okay, that's fine.
My reminder that it was due 59.
Well, it should be. So it should be the day before when it was coming out.
No, I got it last night.
Oh, you just got it last night?
12:28, and it was due at 11:59.
It just showed up. Yeah.
They don't show up until like early in the morning, late at night.
Okay, well, maybe moving it back 2 days will help with that. You'll get it at least before. If we need to, if they still are not coming in time, let me know. We'll move it back another day if they're coming late. So, I don't know what's up with that. So, as of right now, I got them set coming in 2 days before. So, maybe you'll at least see it before it's due. Sorry about that. So that was one thing. And like I said, if you find out that that's still not enough lead time, let me know and I'll move it back more. I would just do like 3 or 4, but I don't want to just hammer you with reminders on it. You know, send too much stuff to you, you won't pay attention to it. So that's how I am anyway. If I get too much junk, I just don't look at any of it. Okay. So, and then the second thing is we're getting close to test time because we're covering our last chapter before test 1. And we're starting on chapter 3 today. So let's decide how we want to schedule that out. Here's my thoughts, and then you can give me your thoughts afterward. Okay? So today is Wednesday, the 8th. So we're going to do 3-1 and at least part of 3-2. We might get through it. It's pretty short today. And then our next class will be Monday the 13th. Okay. Then we'll do 3-3, which is the last section of material for test 1. Okay. So my thoughts are that on the 15th, which is Wednesday, we'll go ahead and do the test review that day, which how I usually do that is I've got a practice test I'll post on Hawks. It's 0 points, so you don't have to do it if you don't want to. Okay? It's just a study tool. You can take the practice test as many times as you want to, but 0 times are required. Okay? But on test review day, what we'll do is we'll just work through all the problems on the practice test together, and then whatever questions you have, you can ask that day. And then, what's our next day? The 20th, Monday the 20th. I'm thinking we'll have what I'll call a Hawks Day. So if you need Hawks help that day, I'll be here. I'll be glad to help with Hawks. If you're all caught up on Hawks and don't need any help or don't have any other questions after the test review or whatever, then just you don't have to come that Monday. And then that'll put test 1 on the 22nd. Okay, but I'm asking. Anybody have thoughts on that? Yes.
It was like the test, like a paper test or the online?
It's paper test, yeah. Just old-fashioned paper test. So things you might think about, like, do we want to flip the Hawks Day and the test review day, or have we got anything major going on? A bunch of you are going to be gone, and it's going to be a big hassle if we do test 1 on the 22nd or anything like that. No big issues. Okay, so that is an option, switching Hawks Day and test review. So it doesn't matter to me which order we do it. Yeah, I'll record on test review day too, though. So you can go back and watch if you want to. Then that's something. I'm sorry. The way it is fine. Okay, so since this will be recorded and you can watch it again if you forget, I guess we'll leave it. That sound okay? Everything will be recorded except the Hawks Day, right? Well, and test obviously won't be, but 3132 we're doing today. 33 will be recorded, and I'll record the test review. And it's just if you need Hawks help getting caught up if you're behind or anything like that. So. Okay. So no major conflicts on 22nd. There. All right, that's what we'll call it then. So we'll say test 1 is going to be on Wednesday, September 22nd. Okay. Let me make myself a note. Oh, thank you. Okay. Anybody think anything else we need to talk about before start doing math stuff? Great. All right. So let's see here. I am recording. Yeah. Okay. All right. So we are moving into a new chapter. Chapter 2, we talked about sets. That's over. Okay. Now chapter 3, we're gonna delve into a branch that we would call logic. Okay. So in section 3.1, we're gonna look at what a logical statement is, and then we're gonna talk about negating those. So we get the name negation, what that means, and then we'll actually talk about combining some logic statements together a little bit. Okay. So the first thing we need to talk about is what we mean when we say a statement, when we're talking about mathematical logic here. So if we're just talking about the English language, and then there are a lot of things that we call statements. Pretty much anything that ends with a period, any kind of sentence that ends with a period, we call a statement in English. So when we're talking about logic in here, we are going to use English. Okay. That's the language this course is delivered in. Okay, but not everything that we would call a statement in English is going to be a statement when we're dealing with logic. Okay, we're a little more restrictive when we're thinking about logical statements. Okay. So the idea here is that when we're talking about a statement and we mean a logical statement or a mathematical statement, which we will in this section, okay, we mean some type of sentence that makes a claim, and that claim is either true or false. Okay, we can assign what we're calling a truth value to it. So it's either true or false. And then got one little extra on here. Says it's not going to be both at the same time. Okay, so, you can end up with some weird stuff. We just need a sentence that's true or false, not both. Okay. That's not always the case with the English language because we have all kinds of weird stuff we do when we speak and write in English. We have things like figures of speech and all kinds of stuff that don't make logical sense, but we can still use them to communicate. have weird, like rhetorical questions when you don't expect anybody to answer it, all kinds of weird stuff. Okay. We're kind of simplifying that for logic. Okay. So the typical way we'll write down a statement, okay, these are two. Okay. Typical way we'll write down a statement is we'll represent it with some kind of lowercase letter. Here we're calling this statement A and statement B, and then we've got a colon, and then we've got the statement after that. So statement A says the car is blue and the cat is black. It's missing a period, so I see that. It's a typo. Okay. And then statement B says first even number is 2. Okay. Those are statements. Because we do have a truth value that we can assign there. So right now, don't get hung up on thinking about whether the statement's true or false. All we care about is that it is one or the other. So we don't know what car we're talking about, what cat we're talking about. We don't have to right now. We don't have to think about that. And even here, the first even number is 2. Okay, if it said the first even number is 3, it would still be a statement. It would just be false. But it would still be a statement even if it was wrong. So that's kind of tricky when you're first looking at these things. We don't care if it's true or if it's false. We just care that it is one or the other. Okay. All right. So what kind of statements would not be mathematical statements? Or what kind of sentences would not be mathematical statements? One we're going to give a name to, and you probably heard it before. That's a paradox. So a paradox is some type of sentence that contradicts itself. Okay. So it says it has no single truth value. That makes it ineligible to be a mathematical statement. An example of a paradox would be like, this sentence is a lie. Okay. So then if you try to think your way through that, if you say that's true, that means it was a lie, so it was false, which means it was, let's see, where you get, okay, you end up going in a circle. It goes in a circle that way. So we want to avoid paradoxes. And then the main other type of sentence that we want to avoid, or that we don't call mathematical statements, usually we're dealing with opinions then. Okay? So like if I say cake is the best dessert, and that doesn't have a truth value to it because it's an opinion. That would mean different things to different people. We could even argue over what cake means on that one. Okay, but it's just an opinion statement, so that would not be a mathematical statement. It's subjective. Okay. So let's look at a few statements and then, or a few sentences, and decide if they're mathematical statements. A here says it is raining outside. What do you think about that one? That one's a statement. Okay. Again, don't get tripped up on thinking about whether or not it's raining outside. That doesn't matter. And we just care that either that sentence is going to be true or it's going to be false. And it can't be both at the same time. So that one is a mathematical statement. Okay. Right, B says beaches are the most beautiful place to vacation. What do you think about that one? Yeah, it's not a statement. Why? Yeah, it's opinion, right? So it's just a subjective thing. What's beautiful even mean? Oh. Okay, so we can't say that has a definite truth value. So B is not a statement because it's opinion. What about C? Today is Monday. What do you think on that one? That one, okay, today is obviously not Monday. It may feel like it. And today's not Monday, but that's okay, because that just means the statement's false, which is perfectly acceptable. But that is a mathematical statement. What about D? We've got a little more complicated here. It says today is Monday and tomorrow is Friday. Let me think about that one. And get the statement. It's either true or false, can't be both, so that one is a statement. And then what's E? I lie all the time. That one's a paradox, okay? That one's a paradox, so it's not a statement. You try to reason your way through that one, you get in a loop. Okay? If you say, yeah, I lie all the time, so that's true, then that means that was a lie, so it was really false. So go around in a circle on that. All right, questions on those? Okay. All right. So, this next little example that we've got is tricky to me. It's one of these things that should be easy because there's like an infinite number of possibilities you could use, but when you actually try to come up with an example, it gets tricky. So it says write down 2 statements of your own. We'll just see if we can come up with 2 as a collective. Okay? We need 1 statement that's always true and 1 statement that's always false. So you think of either one of those? Let's try to come up with one that's always true first. Sun is bright, so you could probably get away with that. See, my mind overthinks, and I start thinking about, well, what about like during an eclipse or something? I guess the sun's still bright, you just can't see it then. So that one. Go to school in Alabama, so yeah, that's true for now, unless you go to school somewhere else. That's what my brain does. But no, that's good. Those are good ones. Okay. What about one that's always false? Think anything? They're tricky to come up with. We actually had one in our last examples that was always false. D's always false here. Because if you look at it, it says today's Monday, so that means it's false today. If it was Monday today, then it would say today is Monday and tomorrow is Friday, so it would be false because that part can't ever have both of these. So that one's actually false all the time. That's pretty good. Am I thinking of any other ones? That's hard. I don't know. It shouldn't be hard, but it is to me. Okay. Sky's green. Okay, so that's okay, maybe. All right. So when we have a statement, the first thing we want to be able to do with that statement, the first thing we want to learn to do is to take the negation of that statement. Okay? Or sometimes you'll hear it called the denial of that statement. Okay? So the idea of a negation is that the negation of some statement will always have the opposite truth value. So if the statement is true, the negation should be false. If the statement's false, the negation should be true. And the part that can make that a little tricky is this always part. So we have to be a little careful there because we want in all situations for them to have opposite truth values. And we don't want any overlap where they could be the same. Okay. The symbol we use to represent a negation, we're reusing a symbol from the last chapter, but remember as we go through chapters, we're looking at different branches of mathematics, so the symbol can mean different things in different branches. So our symbol for negation is the squiggle again, okay. Tilde, and you just read it as not, or you can say negation. Like here we've got a statement that says 5 is a prime number. So the negation of that, squiggle E, would be 5 is not a prime number. That's one way to negate it that works. And because this first statement's true, second statement's false. Okay. So if we have simple statements like this, okay, just throwing in a not somewhere in the original statement is usually a pretty good method of coming up with a negation. Let's think about something else on this one though. What if we wanted to negate the negation? Okay, so we've got not E, and then here it says 5 is not a prime number, and we want to negate that. Okay, that's one valid way of doing it. That's probably the best way to do it. Okay, if we're trying to negate 5 is not a prime number, we could say 5 is a prime number, and we're back to where we started from. So that works. Okay, if you double negate something, you end up with the original. That's fine. Okay. There's another way we can do it too that's a little weird. That's what I wanted to point out here. Okay. In logic, we're going to have some weird grammar things come up. Okay. So we're going to kind of bend the grammar rules a little bit. You think of any other way we could negate this one? We said if we want to negate something, we can just throw in a not usually. Yeah, so that's also valid. Okay, so we could also say 5 is not a prime number. Okay, and that would actually be perfectly okay. We can say 5 is not a prime number. And so your English teacher would be really mad at you for saying that, but logically, there's nothing wrong with it. This is better because this is easier to understand. To just say 5 is a prime number. Okay? But logically, there's nothing wrong with saying not. Okay? Double negatives are okay. Okay? So simple statements, we can usually just throw a not in somewhere and get our negation. Sometimes we'll have statements that are a little trickier to negate. And so we've got a slide with a little table helping us do that. On the little table on the slide, I don't know what I said. So if we have statements that contain what we call quantifiers, then they're a little trickier to negate. So that would be like a statement that says all the students in this room are students at JSU. Okay? Because I said all, that's a quantifier. Okay? Or you could have some or none. Okay? So to negate those, we have to think a little bit harder. So here's a little helper table. So I said all the students in this room are students at JSU. So to negate that, gives us a few suggestions here. We could say not all the students in this room are JSU students. Or we could say some of the students in this room are not JSU students. Or we could say there's at least one student in this room that's not a JSU student. And all those would work in that case. So if we want to negate some, we can use none. And then we got some or all, that's really the same thing. Okay. So just a little bit of something you have to be a little careful about there. Okay. Quantifiers make everything more complicated in logic. Okay. That's just an unfortunate truth. Okay. All right, let's see if we can negate some statements here. Statement A says Melanie is wearing a red raincoat. Sounds good to me. Okay, we can negate that. We can say Melanie is, we just put a not in there, not. Okay, Melanie is not wearing a red raincoat. That would be a negation. That works. Okay. What about B? It says the door is closed. Okay, yeah, I kind of like doing that, but just because you don't get to do it in grammar. You could say the door is not closed. You're probably the more clear way of saying that. What else could we say? The door is closed. Yeah, we could say the door is closed. Okay. All right. What about C? There we got a quantifier. And we got none, so we might have to flip back to our last slide to get a little help. But it says none of the tourists brought raincoats. So some of the tourists brought raincoats, that would be okay. All is a little too strong there. All is just a little bit too strong. We don't have to have all. It's a little more restrictive than we need it to be. So we can say some of the tourists brought raincoats, or what else have we got? We could say there's at least one tourist that brought a raincoat. So the reason why all and none are not complete opposites there is because there's the case where whatever you're talking about only applies to part of the crowd. You have to take that case into consideration. All right, so I like that one. We can say some of the tourists brought raincoats, or at least one tourist brought a raincoat. And what about D? It says I run less than Kara. Okay, all right, I kind of like that approach. I'm good with it. It says Kara runs less than me. I'm good with that. That's not the first way I would think about doing it. I'm good with it though. May think of another way of negating that one. Okay, so that's pretty natural to want to say that, as I run more than Kara, but that's leaving just one little situation out, because we want them to be complete opposites. So the opposite of less than is not more than, it's more than or equal to. So we're leaving the case that we run the same out if we just strictly say more than. So one way we could say it is I run the same or more than Kara. I'm good with that too. There's probably even an easier way to do it if we want to negate it. What's our quick cheat? We just want to be lazy and negate something. Yeah, that's a good one too. We could just say I do not run less than Kara. Okay. Okay. All right, so either one of those. All right. Kara runs less than me is advanced. Okay, but I think that works. Okay. All right. Questions on any of those? Okay. All right, let's do another one with a quantifier. This one says some of the students completed their assignments. Well, that's still some, so you're rewording, which is good. Okay, but we want to negate it. There we go. So if some of the students didn't complete their assignments, that means none of the students completed their assignments. Yeah. So get the negation that way. Okay. All right, and the last thing we want to do in this section is we want to be able to take these simple statements and put them together, okay, to make more complicated statements. Okay. So the way we do that to form what we call a compound statement is we're going to have some key connecting words. Okay. We're going to have 3. We're going to have and, or, and the last one is the relationship, we call it implies. Usually the way we're going to see it worded, unfortunately that one can be worded a bunch of ways. But usually the way we're going to see an implies relationship worded is if something, then something else. And so lots of times we'll call those if-then statements. You can call them conditional statements. Okay. And we're going to want to put these things into symbol form. I told you mathematicians are lazy. We don't want to have to write out a bunch of sentences. We'll just use a few symbols instead. So if we use and, our symbol looks like a capital A, but without the bar across the middle, or you can think about an upside down V. For or, our symbol looks like a capital V. It's just flipped over from and. And then implies is the weird one. If we have an if-then statement or implication, that's what we could call it. You might not be familiar with this symbol, but it looks like an equal sign, and then we have an arrow on the end of it, or like a double-lined arrow. That's what I call it a lot. So that one is implies, or if the thing on the left of the arrow, then the thing on the right of the arrow. All right, so to put these things together, we said we give the statements a lowercase letter name. So here, if we wanted to make a compound statement with and, we would have statement P and then and statement Q. Okay? Or if we were going to use or, I know that's kind of small, sorry. We're going to use or, we could say statement P or statement Q. Something, since we've talked about sets, something you might be able to relate this back to. The and symbol is similar to intersection when we have two sets, right? Intersection is like an upside down U, and's like an upside down V. And then or, the V, is like union. Okay, we have a U shape for union. They're similar ideas. Okay. Similar ideas. And then we didn't really have anything like implies with sets, but okay. Well, let's make some compound statements. Okay. So here we want to use symbols to make statement C in symbols. Okay. So statement A says snow is falling. Statement B says the sun is shining. And we want to use symbols to rewrite statement C that says snow is falling and the sun is shining. So the snow is falling part is A. Sun is shining part, statement B. We want to put these together with and, so our symbol there is the upside down V. Okay. So we would say A and B would be our compound statement in symbols. That one make sense? Okay. All right, we want to do an or statement next, but we've got a little bit of something we have to talk about before we deal with or. In the English language, probably other languages too, I don't know. In the English language, when we say or, we can mean a couple of different things. So if you ask somebody, what would you like to have for dinner, hamburgers or spaghetti? And you're giving somebody a choice, you expect your answer to be either hamburgers or spaghetti. Right? But every once in a while, you'll have somebody that's trying to be clever or witty, and you'll say, what do you want for dinner? Do you want hamburgers or spaghetti? And they'll say yes. So what do they mean then if they say yes? Yeah, they want spaghetti hamburger. They want both. Both. So when we say or, sometimes we mean do you want this or that, or sometimes we mean do you want this, that, or both. And it depends on the context when we just use or in English. Okay? So in logic, okay, and those two ors, those two meanings of or, have different names. Okay? If we're excluding the case where we can have both, we call that exclusive or. Or if we're including the case when we can have both, we call that inclusive or. Okay, so every time you see or in logic, okay, we're going to be using inclusive or. So one, the other, or both. That's what we mean by or in logic. There are times when we want to have this meaning and we specify. If you just see or, it's inclusive or. All right, so now that we said that, let's make an or statement. Okay. So statement P says he will go to the movies tonight. Statement Q says he will stay home to give the dog a bath tonight. And we want to use symbols to make statement R. He will go to the movies tonight, or he will stay home to give the dog a bath tonight. Okay. So, statement P is this part. P. Statement Q, this part. And we want to put them together with or, so that's our V symbol. All right, so to rewrite statement R, we would say P or Q. That would be our compound statement there in symbols. So, like I said, mathematicians are lazy, so instead of writing this big long sentence, we write this. And when we read it, we know it's he will go to the movies tonight, or he will stay home to give the dog a bath tonight. Any questions on that one? Okay. The inclusive, exclusive, or really won't matter until the next section, but go ahead and talk about it. Okay. So we've mentioned it already, but we've still got one more type of statement, and that's that implication relationship. Usually, the way we're going to do them is we're going to say if statement A, then statement B. So lots of times in my head, that's the way I read this notation here. So I'll say if A, then B. Okay. But it also means A implies B, and there are a bunch of other ways you can word this thing. Okay. But usually when you're trying to put it in symbols, it's going to say if something, then something else. Okay. And then we'll end up with that relationship there. Okay, so let's look at one of those. Okay. On this one, statement S says the water temperature on Saturday is below 76.2 degrees. T says you're allowed to wear a wetsuit in the triathlon. And we want to make the statement Q in symbols that says if the water temperature on Saturday is below 76.2 degrees, then you are allowed to wear a wetsuit in the triathlon. So this part, that's statement S. This part is statement T. So the piece we're missing is the if, then. So we want if the first one, so S, and then our double line arrow, T. Okay. So if the first thing, then the second thing. Sounds a little weird. Okay. That's what we'll want there. Okay. And in Hawks, it'll give you a little keypad with this thing on there. Okay. And on some of it, it might even fill it in for you. Okay? But if you need to type it, it's not on the keyboard, on the standard keyboard, so let you fill it in there. Okay. All right, let's practice, make 3 more of these, okay, and we'll be done with this section. It's not a long section, so. See if we can make these. So we've got 3 basic statements, and we're going to make 3 different compound statements. So we've got statement A, I'm hungry. Statement B, I'm tired. Statement C, I'm in college. Okay. So how can we make statement number 1? We want to do it in symbols. Okay. So what do we need? We need the I'm hungry part. That's A. And then we're using and. Which symbol is that? Upside down V. And then I know it's worded a little bit different, but the tired part, that's B. Okay? It's okay for the English words to not be exactly the same as long as the meaning's there. Because this sentence we could reword, right? We could say I am hungry and I am tired, and it means the same thing as saying I'm hungry and tired. Okay? So that's okay. That works. Same meaning, even though the English might be a little bit different. All right, what about 2? I'm hungry or I'm in college. Okay, we need A for I'm hungry, or is the V symbol, and then C for I'm in college. Okay. And 3 throws us a little bit of a curve. We need I am tired and not in college, so I am tired is statement B. We need and. Then how do we get the not in college part? We got a squiggle, statement C. So statement C is I'm in college, so we negate that, get I'm not in college. Okay. So we've got B and squiggle C. B and not C. Questions on those 3? Good with them? Okay. All right. That's 3-1. 3-2 is not very long either, so won't take us too long on that. Okay. So in section 3.2, we're looking at these things called truth tables. So now we're actually being concerned about whether our statement is true or false. Okay. In 3.1, we just cared that it's one or the other. In 3.2, we're going to keep up with whether our statement is actually true or is actually false. Okay. So if you just have a simple statement, like we have a statement like my shoes are gray, okay, that's easy. We could say, well, looks like they're mostly gray, so we'll go with that and say that's true. Okay. Or if I say my shoes are blue, then we'll say that's false. Okay. But if you have more complicated things, like we're making when we start putting ands and ors and if-thens in there, it can be complicated to kind of try to keep track of what's going on. Okay. So in that case, if we have a logical statement that's very complicated at all, then these things we call truth tables come really in handy. Okay. It lets us just break it down one piece at a time to figure out the truth value of a whole statement. Okay. That's where we're headed. Okay. Okay, so what a truth table is, we're just gonna have a table, okay, and each row is going to give us a combination of truth values for each individual statement. Okay. So they're made up with rows. When we're filling them out, it's going to be a lot easier to do a column at a time. Okay, and hopefully I'll be able to show you that in just a second. Okay. But each type of connecting word out of our three we have has a different rule for what happens to the logic value. Okay. So if we take two statements and put them together with and, the logic's going to be different than if we take two statements and put them together with or. Okay. So, and the same thing's true with implication. So we kind of have to look at what the truth table looks like for each one of those types of connecting words there. So the first type of compound statement we get is when we use and. Okay. We'll call that a conjunction. I know in English you call any of these connecting words conjunctions, but in logic, when we use and, that's a conjunction. Okay. And a conjunction or an and statement is only true if both pieces of it are true, okay? If both simpler statements are true. Okay. Otherwise, it's false. Okay. So that kind of makes sense if you think about it. All right, if I say I am 40 years old and I'm 10 feet tall, okay, the only way that statement's true is what? If both things are true. If I'm 40 years old and I'm 10 feet tall. Okay, if either one of those two things are not true, then the whole statement's going to be false. That's what our truth table shows us. So here's what the truth table can look like. This part, we're just filling in all the combinations. Okay? So this part's not complicated. All right, we're just trying to make sure we've got all the combinations of truths and falses together. So the way they're going to look is whatever the second statement is, we'll flip it from true to false, and then the other one's true, true, false, false. That part's no big deal, okay? Because we're just accounting for all the possibilities here. The part we want to focus on is this last column, because that gives us what we end up with when we're doing a conjunction, when we're using and. Okay? So what this is telling us is that if we're combining two statements together with and, if the first statement is true and the second statement is true, then the whole statement is true. If we have any other combination, that whole compound statement's going to be false, right? So if the first part's true but the second part's false, that compound statement's false. First part's false and the second part's true, the compound statement's false. If the first part's false and the second part's false, then the compound statement's false. And this row's what? I'm not 40 and I'm not 10 feet tall, so not that one. Okay? Whole thing's false. Okay? So that's and. The only time an and statement is true is if both statements, both simpler statements, are true. Okay? That's a rule. Any other combination is going to be false. All right. Okay. Our second connecting word is or. If we use or to combine two statements, that's called a disjunction. Okay. And I don't know that the way they have it worded is the best way to remember. It says a disjunction is always true unless both statements are false. To me, it might be a little easier to remember the rule there. If you say, well, no, that's okay. Maybe that's all right. It's always true unless both statements are false. Oh, so maybe usually the way I keep it in my head, it's only false if both statements are false. Any other time it's true. So that way it words it kind of the same way as the other one. Okay, so then you can say and statements are only true if both statements are true, or statements are only false if both statements are false. Okay. It can be a little tricky to get the rules straight on these to start with. So let me get that out of the way because we've got the truth table here somewhere. There we go. So what that's saying, and remember, these are just all the combinations. This is the part we want here. So it's saying if both pieces are true, the whole statement's true. If just the first piece is true, the whole thing's true. If just the second part's true, the whole thing's true. The only way it's false is if both pieces are false. Okay. So in my head, I think about this is saying, is this one true or is this one true? So yeah, so it's true. Okay. And if you say no, then it is false. Okay. Okay. So that's that one. Okay. And then we got the conditional, okay, and unfortunately the conditional is the troublemaker. Okay. Got an if-then statement or a conditional statement or the implication, you can call it that too. If we put two statements together with a conditional, or in a conditional statement, this one's hard to remember, okay, for me anyway. The only way a conditional statement is false is if the first part is true and the second part is false. Okay. Yeah, the only way a conditional statement is is false, is if the first part is true and the second part is false. Okay. And we're gonna go through and make the table for this one just because it's a little more confusing. And then I'll give you a little bit of my spiel after that. Okay, so let's see if we can think our way through one here, and we'll fill out our table here. So this one gives us a conditional statement. It says, if it rains, then we will stay home tonight. Okay, so we're gonna let it rains be W, and we'll stay home tonight be Z. We wanna make the truth table. So this is how we fill out a truth table, okay? We've got all the possible combinations here, and then we just think about our rule, okay? So our rule says the only time a conditional statement is false is if the first part is true and the second part is false, okay? So that's what I look for. This part's missing, hang on. So the case that's mentioned in our definition is the second row. So the only time this thing is going to be false is when the first part is true and the second part is false. So I know my value here is going to be false. Okay. And then these other three have to be true. Okay, that's by the definition. That's by the definition. If you think your way through it, it may help. So let's actually think our way through that. I could say, if I'm 50 years old, everybody in the class gets an A. Okay. So if it turned out I was 50 years old and everybody got an A, that would be true. Right? Okay. The only way the statement could be false, the only way I could lie to you, is if I said if I was 50 years old but everybody did not get an A. That would be a false statement. Okay. These other two are the weird ones. Okay. These other two are where the first part is false. This has a fancy name. We say these two are vacuously true. All that means is if you start off with a false statement, you can say whatever you want to after that. Doesn't matter. Okay? So if I'm not 50, I can tell you, they're going to open a new dorm on the moon. Okay? It doesn't matter what I say after I start off with a false statement with the if-then. Okay? But makes it a true statement because I started off with a false statement. Okay? That's hard to wrap your head around. Where did it? Okay. I'm not 50, sorry, so. Okay, that was a tricky one. Okay. We're not gonna have a lot of those. But I do know that one's a little trickier to remember. All right, so let's look at filling out another truth table. Okay. And we're just using our 3 rules. Okay. And our 3 rules here. Let's look at this one. Okay. So we don't even care what all that says. Okay. Our end goal here, what it said in the directions, was to fill out a truth table for this statement, A or not B. Okay. That's hard to wrap your head around what the truth value is going to be there. So what we do instead is we take it one piece at a time. Okay. So we're just going to look at this column first. Okay. The not B column. Okay. So when I'm doing the not B column, the only other column I'm looking at is the B column. Okay. Because I know the negation of B, what do we know about its truth value? Has to be what? The opposite of B. Okay. So if B is true, not B has to be false. And we'll go down to the next one. If B is false, not B has to be true. Go down to the next one. If B is true, not B has to be false. We'll go down to the next one. If B is false, not B has to be true. Okay. So all I'm doing there to do a negation column is I'm just flipping. I'm just doing the opposite of whatever was in the B column. Okay. That, you with me? Doing the opposite of B? Okay. Now to do the last column, I'm going to look at 2 columns because we've got a compound statement, but I'm only going to look at the A column and the not B column. So let me highlight those here. So I'm looking at this column and this column. Don't care about that middle one. I'm done with it. And we want to take these 2 and put them together with OR. Okay. So I want this truth value or this truth value, and that'll tell me what to put here. Okay. So as I go across, I'm looking at the first row. It says the first one is true, the second one is false. So with OR, what happens there? That's the tricky part. Right? So an OR statement is only false if what? Both statements are false. Okay. So an OR statement's only false, sorry. OR statement's only false if both statements are false. So on the first row, I've got true, false. That's true. Second row, I've got true, true. That's true. On the third row, I've got false, false. That's where the alarm bells go off, okay? That's the only time an OR statement is false. And then on the last one, I've got false, true, so that's true. Okay? Because it told us on an OR statement, an OR statement is only false if both statements are false. So we only have that one time, and it's on this third row. Okay. So that's our truth table for that compound statement. Okay. Questions on that one? The parts you got to remember, about the truth value of an AND statement. The statement's only true if both statements are true. You got to remember about an OR statement. The statement's only false if both statements are false. And then we do have the implies in there, okay, that'll pop up occasionally. and it's only false if the first part's true and the second part's false. Okay. And then the only other thing we used there was that if we do the negation, it's the opposite. Negation is the opposite. Okay. There's, let's see. Two other things. So we're going to do another truth table. We're going to look at, that's what we just did. There's a little summary table in the slides. There, if you want it, it's the same stuff we've already talked about, but it is there in the slides. Okay. Here we got another statement we're going to look at. So here's a compound statement made by John Wooden, okay? Famous basketball coach and player. Okay? It's old though, it's back in the day. All right, so the statement is if you're not making mistakes, then you're not doing anything. Okay. So if you're going to make a truth table here, one thing we got to look at is that we've got a not on both of these. So the original, without the negation, it would be if you're making mistakes, then you're doing something. Okay? So we've got a negation on both of these. So we're going to have to negate both pieces on our truth table. And then we want to put the whole thing together, and it's an if-then statement. Then. So the way we would set the table up, okay, we would have our options for A and B, but then we got to have a column for negating those because they both had a not on them. So let's do our negation columns. They're easy. Okay. So for the first one, for not A, I'm just looking at column A. So A was true, not A would be false. A was true, not A would be false. A was false, not A would be true. A was false, not A would be true, right? They're just opposites. Okay. The second column we need is the not B column. So I'm just going to look at column B. We're just doing the opposite. So if B was true, not B would be false. If B's false, not B would be true. B was true, not B would be false. And then if B was false, not B would be true. Okay. So we got those. Okay. So the last column, we're looking at not A, not B, and we're trying to put them together with the if-then rule or with the implication rule, okay, which is the trickier one. Okay. But as far as looking at the table, I'm only looking at two columns when I'm filling out this last one. I'm just looking at this column and this column. Okay. And I'm putting them together with implies or if-then. Okay. So our rule or implication for if-then statement, conditional, is it's only false if the first part is true and the second part is false. So if I'm doing this, if I remember that rule, I'm just going to look to see if I see that happen. So I see first part is true, second part is false right there. Okay. So that's the only time an implication is going to be false. For the other ones, we only have that true and then false one time. So on the other ones, it's got to be true. We don't have to think hard about the other ones. Questions on that one? That one's the trickiest one there when we got if then. And then it'll take a little bit of practice to learn the other rules. Okay, you need and, or, and then if then. Okay. I only got one other thing to talk about. We'll be done. We'll get out of here early. Okay. So one other thing to talk about. And that is if we have a compound statement, or really just a statement, that is always true, okay, we give that a special name. It's called a tautology. Okay. Tautology. So if no matter what, the statement's going to be true in all possible circumstances, that's tautology. So on some of the problems in Hawks, it'll get you to do that like one column of the truth table, and then it'll say, is this a tautology? The only way it's a tautology is if you have all T's. If it's all true, then it's a tautology. If not, it's not a tautology. So let's look at one that works out that way. And I have no idea what this name is, I'm sorry. Okay. It says construct truth table for the following compound statement. I think it's Emory, maybe. It says next year Emory can take physics or he cannot take physics. Okay. So here, let's see how they label. They label it statement C. The thing to notice is on this one, whatever we call that, our book's going to call this statement C. I don't know why they didn't just do A or something. Okay, but then what's the second part? It's cannot take physics. So that one's going to be not C. And then they're combined with or. So if we're making a truth table, this one's shorter because we've only got one statement we're working with. So the choices for statement C would be it's either true or false. So then we need the negation of C. So it's just the opposite. So true goes to false, false goes to true. And then for the last column, we're combining with or. So an or statement is only false if both statements are false. Here we've got one true statement, so it's true. On this one, the second one's true, so it's true. So on our final statement, we've got all T's. So that one is a tautology. It's tautology. Now, since these are all T's, it's a tautology. Tautology. All right. Okay. Questions? Good, Greg, get out of here. All right. Let's see, where'd the sign-in? Oh, I got it up here. I'll put the sign-in sheet on the front table if you missed it and get on your way out. Okay. I will see you next week.